Inside a modern AI data center, every component is optimized for a singular goal: maximizing intelligence. But that immense power generates a devastating byproduct: heat. Deep space exploration changes the variables. Outside Earth's magnetosphere, probes must operate on incredibly rigid power budgets, often relying on systems that provide only a few hundred watts of electricity to last for decades. Attempting to run high-fidelity AI models in these environments induce optimization psychosis. The system tries to maximize its understanding of the universe, but in a power-starved state, this rapid computation immediately triggers thermal throttling and total system collapse. Traversing the void requires resigned architecture. This framework prioritizes structural survival above all else, abandoning sensory fidelity the moment the thermal load becomes unsustainable. Behavior OS serves as the foundational software framework for this approach. It is an architecture engineered exclusively to maximize endurance. The system operates on three core pillars. First, semantic lobotoming. Second, render taxes. And finally, adaptive fidelity. These pillars impose hard physical constraints on the digital agent. They prevent the software from attempting to process the full complexity of its environment, forcing it to drop high-level reasoning to preserve its hardware. Behavior OS functions as a semantic flight computer. It manages meaning and memory the same way a traditional spacecraft manages fuel and oxygen. This load diagram illustrates proof of friction. Simulation fidelity is paid in hardware heat. The system tracks the void margin, the gap between attempted processing and safe rendering capacity. Breaching this threshold triggers liquidation, stripping away textures and Z-axis geometry until the hardware cools. This liquidation ensures that peak load never leads to hardware collapse. The agent survives, but it is forced to perceive a lower resolution version of reality. Thermodynamic compute turns hardware limitations into foundational physical laws. Traditional game mechanics are replaced by the reality of progressive asset degradation. We execute this structural exhaustion at the shader level. By linking a global variable to the world position offset, we simulate physical fatigue. As the compute load increases, the geometry literally sags. Temporal dithering algorithms phase out textures gradually. Hard asset flickering creates power-hungry input-output spikes. Dithering ensures a low-energy transition from high to low resolution. At the logic level, AI behavior trees implement futility loops. Agents execute repetitive, useless rituals solely to clear internal entropy buffers and reduce processing pressure. Live engines cannot safely write back to their own repositories. Direct modification of the source control during runtime creates a circular dependency that will crash the world state. We solve this by decoupling the command and control process. We stage heavy assets externally via getLFS, and the engine independently polls an asynchronous database for simple pointer values. Simulation stability relies on this strict isolation. The agent's logic must remain separated from the engine's real-time rendering demands. If the system drops to 1% available compute, it triggers the golden hour protocol. This initiates hierarchical asset salvation. Every piece of functional geometry, the floors, the walls, and the NPC agents, is cold entirely. The system channels its final jewels into a single static skybox. It abandons real-time sensory processing and flies blind on a pre-calculated compressed memory of its destination. The protocol prioritizes the maintenance of a cheap, isolated simulation over an attempt to survive in an expensive, complex reality. Reconciling this software with physical reality requires addressing the wattage gap. Surface fission, or RTGs, provide a steady but low baseline of power. They cannot accommodate the massive power spikes required by consumer GPUs. Surviving these wattage limits requires replacing power-hungry data center hardware with compact embedded edge compute modules. To run on this limited hardware, the agent relies on semantic lobotomy. As power degrades, the system offloads heavy contextual memories into cold storage. Using pointer stubs, the agent maintains a hard-coded spine of immutable core behaviors in active, low-power memory. Endurance in deep space relies on this systematic, localized forgetting of high-fidelity data. When we integrate these software modules into a spacecraft schematic, we create a unified survival mechanism. The entire probe functions as a semantic flight computer. It constantly monitors thermal pressure, dynamically throttling non-critical modules to preserve the central identity kernel. This probe never attempts to map or optimize the universe. It prioritizes its core directive above all contextual awareness. To achieve resilient, autonomous compute in the vastness of deep space, the system relies entirely on the engineered capacity